This is a demo video for lab5, and this is part 1. In this part, we need to build the ALU model and extend this ALU to have more function, such as subtract and or and shift. In this part, we just use a pure block to build this function. So the most important thing I think is we need to use this. We don't need to use the clock as a trigger in here, because after all it's combined logic, so we just need to use this program. And the first thing we need to do is add. It's very simple. When the control signal is on 0, is 30, we need to add A and B, and the overflow is this logic. So we all study it in 457, so I think it's very simple. And also subtract is the same. In Vlog, we don't need to use other implementation, so we just need to say that A minus B, and the overflow is here. So the third and fourth control signal is A and B, and A or B is also very simple, and XOR, and the compare is when A is equal to B, the signal become 1, otherwise it becomes 0. So I think it's also very simple. And the shift is left shift 1 bit. So this is combination logic. As the instruction said, we will have a register after the ALU. So we use this program to build a D flip-flop as a register, and store the result and pass it into the output Z, and overflow OVF pass it into the overflow. So now we can see the simulation to check its function. First, we can see the test bench. We can see the test bench first. So It seems like it will take a little bit time. Uh, we okay. So in here we can see that in 100 nanosecond the reset is put up and the state to from 0 to 1, and the clock have a positive age after 10 nanosecond. So we can yeah. So when a control signal is all zero, it means that we do add, and so it seems like the function is correct. We can see it in this form. So 5 plus 3 is 8, and then we can check if we can do the overflow test. So when A is this value and the B is 1, we will have an overflow. So the overflow is set to 1. So let's prove that the overflow test is passed. And now let's check the fraction. 10 minus 4 is 6. And also we can check the overflow. So this value minus 1 overflow pull out to be 1. So the subtraction is also works very well. The control signal, when control signal is 2, it means that A and B. So B is all 1 and A is all 0. So let's see, the output should be all 0. And when the control signal is 3, it means that this is all. So when the B is all 1 and the A is this value, and the output C should be the same as B. This is XOR, and this is XNOR. And the final one is a shift. We need to left shift 1 bit from to A, from A to Z, and it seems like it can perform properly. So right now we can prove that every function works very well. And in lab6, we need to insert this ALU model uh, to EX stage. So I think in this step I include every information I need. So thank you very much. This is a demo video for lab5. My name is Yijing Chen, and I will show the part 2 and part 3 in lab5. First, we need to build a register file. So in this part, we just use the pure block because if we use the schematic, it will become a little bit complex. For example, if we draw a schematic to build a 64-bit register file, we need to at least 64 D flip-flop. So we will waste a lot of time. So in this pipeline, we build most model in pure block. However, we draw the skeleton of the pipeline. We use a schematic, and also we need to draw the instruction memory. It's almost the same. However, in this part, we have the second reason. That's why we use the block instead of schematic, because we can very easily store this value in initial block. However, if we use the schematic, it will become very complex to store data into this model. It will waste a lot of clock and make things become very complex. However, if we use the pure block, it will waste much more resources in NetFPGA. But I think we can do some optimization after this club. And now let's see the data memory. In this part, we just need to store some value. We store 5 value, 1, 0, 0, 0, and 100 in the first 5 location in main memory. And I think it's almost the same. So now let's look at the skeleton of pipeline. This is the IF stage. In this stage, we have 3 components. First is PC value register and PC adder, and the most important is the instruction memory. we introduced it in before. So now let's look at the PC value register and PC adder. PC value register is super simple. It just like a D flip-flop, and it passed 9-bit value, and it store the current PC value and pass the next PC. It actually accept the next PC value and pass the current PC value, and PC adder is also very simple. Is increment, do a increment in this step. The current PC value plus 1 is next PC value. So now we all know that all the component in the instruction fetch stage, and the IFID register is register. So when the positive age come and the reset is 1, it will pass 32-bit instruction to next stage in ID stage. Now we can know that the accept 32-bit register instruction, and this one is write register enable. We don't need to do anything, and we just need to pass this bit to the next stage, and write enable, write address, write data. Right now we don't do anything right now. The first we can see that in here the first instruction we need to load the first load the first value from main memory to the third location of register file. So we can know that right now right now we can know that the register file we accept these two value, and we pass these two value to next stage, and these two value indicate the address of the main memory. So it will connect to the main memory stage, and the last one is the write register. It indicates the register the location where we need to write the value from the main memory. And this one is EX stage. Right now we don't do anything in this stage because we don't need to insert the ALU in lab5. I think we will do it in the lab6. So the register is almost the same. So we skip this stage, and in here we have a register, write register enable from the previous stage, and we don't need to do anything. This single bit is passed to the write back stage, and we don't need to do anything. However, we need to read some data from main memory. The write memory enable is the first bit of our instruction is 0, so it means that we don't write anything into the data memory. However, instead, in this part, it indicates that we need to read this address from the data memory. I think is the first location of data memory. The value is 1, and the write data is also make no sense because we don't need to do store word. And now the data from this address is flow to the memory and the write back stage register and passed to this port. So these two is connect together, and these two is connect together, and these two is connect together. This indicates that right now we need to read the value from write back stage and store it, make it enable, make the register file write enable, and this signal is write data. Write data means that the data from the main memory is the first location's value. It flow into the register write data port. So now it accepts this value from the main memory. And the last value is the write register. It indicates the address of the register file. So it indicates that we need to write this data to this location. So now we successfully do the load instruction, and the test bench is also very simple. We just need to make two signals. The first signal is the reset. We set it into high in the after 100 nanosecond, and the clock signal is keep become 1 and 0, and Now let's see the simulation. The first one we need to see is uh, next PC value. So in this stage, uh, reset signal is 0. So it indicates that the system is freeze, and after the reset signal become high, everything start to work, and the next PC value indicates that 0 plus 1, 0 is our current PC value, and write enable value become high after several clock, and the write address become 2 and 3. Uh, we can we can see the previous instruction said that we need to write into the register location 2 and the location 3, which means that the third and the fourth location in register file, and the write data from the main memory is the first value of the main memory is 1. Uh, so we write the list value to register file. We can see that uh, 0, 1, 2, 3. So in this clock, we write the value from main memory, and after 1 clock, we do another instruction. We store this value into the next location in register file. So I think this can prove that our pipeline can do some basic function. I think it's the uh, everything I need to include. Uh, our teammate will uh, do another step in the next stage. So thank you very much.
Hello guys, this is Journey Wei from Team 10. I will be demonstrating part 4 of lab 5, which is integrating our pipeline processor into the FPGA platform. The key idea is that we take the pipeline we built and simulated in part 1 through 3 and place it inside the NetApp FPGA so we can load programs on the processor and verify results from the Linux command line. First, I will load our custom bit file onto the NetApp FPGA. You can see from the output that the project name is Rogue and the device ID is 103, which confirms that this is our processor design, not a reference router. Now I will start the routing demo so that the nodes can communicate. Before testing the processor, let me verify then the router still works. A plugged-up module uses a pass-through design for the data path, meaning packets flow through without any modification. All nodes can ping each other. This is important because it proves that adding our processor module does not break the NetFJ routing functionality. The pass-through is just a direct write wire assignment from input to output. Now let me check the processor's register. We designed 6 registers for the interface. For a software register that we wrote to command, address, write data high, and write data low. For our hardware registers that we read from, read data high and read data low. Let me show it. You can see command address, write data high, write data low, read data high, read data low. Registers are read 0, which is the expected initial state. This confirms that the generic Rex module is currently connected and the register addresses matches between our parallel script and the hardware. The address .and 2000100, which was assigned by the NetFG compiler based on our blog XML configuration file. Before loading the test program, let me briefly explain how the interface works. Our processor has an instruction memory and a data memory provided in simulation. We could preload these memories directly, but on real hardware, we need a way to write data into them from the outside. This is what a register interface does. The command register tells the hardware that what operation to perform. Command 1 means write to instruction memory, command 2 means write to data memory, and command 3 means read from data memory, command 4 starts the processor, command 5 stops it, and command 6 resets it. There is a memory multiplexer inside the prototype, and when the processor is stopped, the multiplexer connects the memory to the register interface so we can load programs. When the processor is running, the multiplexer switches to the pipeline so it can fetch instructions and access data. This way, the same memories are shared between external control and pipeline execution. I will load our test program. This is the same 6 instruction program from part 3 that we verified in installation. Let me explain what was just loaded. First, we initialize the data memory. Address 0 contains the value 4 and address 4 contains the value 100. Then We loaded 6 instructions. Instruction 0 loads the value from data memory address pointed to by register 0 into register 2. Since the register 0 is initialized to 0, let's read data memory address 0, which contains 4. Instruction 1 does the same thing but writes to the register 3. Instruction 2 through 4 are knobs, which are necessary because of the pipeline delay. The data needs 3 cycles to propagate from the memory stage back to the register file before subsequent instructions can use it. Instruction 5 stores the value of register 3 into the data memory address pointed to by register 2. Let me verify the initial state of data memory address 4 before running. You can see that the mem4 is now 100 in hex. Oh, it's 64 in hex, but actually it's 100 decimal. This is the value we just loaded and we expect it to change to 4 after the processor executes the program. Now let's run the processor. The processor is now executing. The pipeline is fetching instructions from instruction memory, decoding them, processing data memory, and write result back to the register file. All in hardware at FPGA clock speed. The 6 instructions complete almost instantly, but I'll wait a moment to be safe. Now, the processor is stopped. The memory multiplexer has switched back to the external control, so we can read the result. Let's look at the result. Data memory address 0 is still contain 4, which is correct since we only read from it. Data memory address 4 has changed from 100 to 4. This confirms that the processor successfully executed all 6 instructions on the real FPGA hardware. What happened internally is the pipeline loaded the variable from data memory address 0 into both register 2 and register 3. After the knob delay, instruction 5 used register 2 as the address, which is 4, and store the value of register 3, which is also 4, into data memory address 4. So the original value of 100 was overwritten with 4. Let me also show the final register state. And let me confirm that the router still works after all these operations. Still works, the pass-through data path was unaffected throughout the entire process of loading, running, and verifying the processor. Okay, that's all for my demo. To summarize, we successfully integrated our four-stage pipeline processor into the NetFPGA. The register interface allowed us to program the instruction and the data memories, start and stop the processor, and read back result from the Linux command line. The pass-through data path ensures normal routing is not affected. The test program executed correctly with data memory address for changing from 104 as expected, matching our simulation result from part 3. Thank you.